Hi everyone, my name is Michael Hackett and I am researching a cyber anomaly detection platform for MCAS Miramar. My client is Dr. Preetha Tulasiraman with the Naval Postgraduate School. The energy management system at MCAS Miramar is being upgraded to support remote command and control of distributed energy assets around the station. Verizon's 5G non-standalone network will be leveraged to integrate the assets. Internet of Things transducers will transmit and receive messages to and from the Energy and Water Operations Center using either 4G or 5G wireless dongles, depending on the node covering the device. Since the integration involves commercial infrastructure, there is a concern about newly introduced cybersecurity threats to the system. Unfortunately, 5G non-standalone architecture does not support a cyber anomaly detection mechanism. To bolster cybersecurity for the project, researchers from the Naval Postgraduate School are developing a prediction-based cyber anomaly detection platform. Various unsupervised machine learning approaches have been evaluated for anomaly detection using both synthetically generated 5G wireless data and Modbus TCP/IP data captured on the wired side of the system. Each model was trained with several data representations and tested using carefully crafted synthetic anomalies. Models were built using the TensorFlow and scikit-learn data science libraries. The Pandas data analysis library was used for data processing and anomaly generation. Visualizations were created using Seaborn and Matplotlib, and the IDE of choice was Spider. The Anaconda data science platform was used to set up this environment. The first experiment expands on a previously completed distributed denial of service experiment by scaling the data and testing two new models. Both the basic autoencoder and convolutional variant showed good performance across the board. Scaling the data had the biggest impact on the k-means model, which performed poorly with unscaled data. For novel device detection, select traffic flows were set aside and excluded from training. 3 feature representations were tested: size stats, size and TCP stats, and size stats with TCP and time to live stats. All 3 included data rates. All models performed well with the Modbus data, but 5G experiments showed poor to mixed results. Scaling had the biggest impact on tests without header statistics. Generally, including header statistics improved model performance. For man-in-the-middle detection, models were trained on ARP requests and responses. Responses from the gateway's IP address but not its MAC address were generated and marked as anomalous. Note that since this approach uses specific addresses, a change in network topology would require model retraining. The basic and convolutional autoencoders performed well. K-means failed to detect this attack when broadcasts were included. It still underperformed with them removed. Scaling the data did not impact performance. The Modbus data contained register values with query responses. Models were trained using these values and their associated unit numbers. Tests were performed using random data within the same ranges as the responses and unit numbers. Although tests were random, this experiment showed there is a learnable pattern to the query responses. All models performed well, but k-means scored lower than the others with unscaled data. These experiments showed that targeted anomaly detection for the hybrid system can be plausibly achieved using unsupervised techniques with tailored feature sets. The basic autoencoder proved sufficient in all cases. It was not outperformed by the other models. K-means had the poorest performance overall. Scaling the data only improved scores in some cases. However, this is still considered good practice. Future research will focus on feature representations specific to data from the completed system. Final datasets may show different results. Thanks for watching.